Okay, so what is this course about? We are mainly talking about electricity, magnetism, light, and then modern or quantum physics. So we're going to start with electricity. That'll be our very first topic. And what I want to start by doing first, we're going to talk about electric force. Okay? Now, force should ring a bell from Physics 1. There are a lot of forces in Physics 1, and this is just adding a new one to the list. So let me remind you from Physics 1 what kind of forces we might have introduced. Now, if you've taken physics with somebody else, I may not use the same notation, but these should ring a bell. Force of gravity, also known as weight sometimes. We talked about tension, that's the force from a rope or a string. We talked about normal force, that's the force from a solid surface, like an inclined plane or something like that. We talked about frictional force. We have two types of friction, static and kinetic. And we have maybe the spring force. That's another one. You may have talked about something called buoyant force. So it's the force from a fluid that holds things up. And here's the thing. All of these forces, all besides gravity, all of them depend on the cohesion of atoms to other atoms and molecules to other molecules. And the thing that's ultimately responsible for that is the electric force. So you can actually say that these are all special cases of the electric force. Okay? So they're basically just applications. They're kind of situational special cases of the electric force. The only one that is not an electric force is gravity. Okay? So these are basically the two forces that we have entertained so far in all of physics. You may know that there are only 4 fundamental forces in the entire universe. These are the first 2. The other 2 relate to the nucleus of an atom, not something we need in our studies for the moment. I'll maybe touch upon them briefly later in the course. But what I'm trying to imply here is that understanding electrical force is a very big thing. Okay? It's a very fundamental thing. And once we kind of understand the electrical force, then we could, of course, use all of our stuff. The big thing we used in Physics 1 was Newton's second law, right? F net equals ma. And what does that say? It says that if you know the sum total of all the forces that act on something, so this is the sum total of all the forces, a special process called vector addition is needed to do that. It's not just as simple as adding numbers, right? It's kind of a pain. It requires being really fluid with SOHCAHTOA and all that stuff, breaking vectors into components. Is this ringing a bell? Okay. So once you have all those forces, you add them all up. All the forces that act on something, their combination is called the net force. We call it net force, total force, overall force. And that will cause an object to change its motion. We call that acceleration. Things don't accelerate on their own. They accelerate because they are forced to do that. And the amount of acceleration you get will be related to how much mass. So that's how much inertia something has, how stubborn it is to changes that you're trying to make. If you apply a force to a big mass, it'll accelerate not very much. Okay? So, that right there is kind of where we're going, and just like all of these forces kind of had rules and equations, we're going to explore what is the equation for the electrical force. So let me back up for a second and talk about what all normal matter is made out of. Okay? So this is all normal matter. So normal is of course a, it's a loaded word, but everything that, when I say all normal matter, I mean your entire body, everything in this room, everything you can see, everything you basically will see is normal matter. It's all made out of just 3 different items, okay? So, name, let's list them first. All atoms in normal matter are made out of protons, electrons, and neutrons. So if you've taken even the slightest bit of science, you probably know that the protons and neutrons, they go in the middle of the atom. They form what's called the nucleus, and then the electrons are on the outside, right? Sometimes you see a more simplistic model where they're kind of orbiting like a little mini solar system, or for those of you that have gotten far enough in chemistry, you talk about something called orbitals, which obviously derives its name from kind of going around, but they're more like these fuzzy clouds, right? Is it ringing a bell? Okay. So, those are the constituents of normal matter. So, let's go ahead and say we have this kind of, some kind of hammer where we can break apart an atom that's made out of these things, and here's what we find. A proton, it's like this. If you take a proton and put it at a, reasonable distance away from another proton, what you find is that they will repel each other. So they will accelerate, and there must be, of course, a force behind that. So that's electric force. We give a name to the phenomenon because this is the thing that the particles that make up things, they actually exhibit this behavior, and we need a way of classifying them. Likewise, if you have an electron, they will also repel each other. One thing I want to point out right away is I've drawn the electron much smaller. The masses of these guys are not the same. So we need to talk about their masses. Let's put down their mass in kilograms. So the mass of a proton is 1.67 times 10 to the minus 27 kilograms. That, by the way, is the exact number you should use. If you start kind of being loose with how much round off you use, you may occasionally get caught with WebAssign. WebAssign obviously can't read your mind that you did it right, but you used a different rounded off value. So this is our official value in the class. You'll find it on the formula sheets, the exam formula sheets that I've already posted for you. And if you use that value, then if you're getting it wrong in WebAssign, that's not the issue. It's not that you're using a slightly different round off of the mass. Okay? That goes for any physical constants. The ones that are on the formula sheet are the official values for this class. An electron is 9.11 times 10 to the minus 31 kilogram. That's about 2,000 times smaller. Okay? So significantly smaller. Their masses are not the same. Okay? The mass of a neutron is approximately the mass of a proton. And that's about where we'll call the end of the day for our analysis, though the fact that it's approximately but not exactly has a whole bunch of other interesting physics along with it. Okay? Okay, so that explains why I have drawn them different sizes to kind of, so that you remember that they're not the same mass. And so far what we seem to have found is that protons and electrons, they don't like each other, okay? Or I should say protons don't like other protons, electrons don't like other electrons. There was a repulsive force seen there. So what about proton and electron? We find that those attract. So if you see two things attracting, you may say, well, couldn't that be gravity, right? Gravity attracts two things just because they have mass. Well, if you worked out the details, you would find that the attraction is way too strong for considering what their masses are, and so you have to still conclude it's something new. So even though it's attractive like gravity, the attraction is way more than it should be with gravity, so that is also a new phenomenon. And what we're doing is we're bundling all of these under what's called the electric force. Okay? I should mention, I haven't said anything about neutrons. Neutrons don't participate in the electric force at all. Okay? So if you put two neutrons reasonably nearby each other, they don't attract or repel. If you put a neutron at a reasonable distance from a proton or electron, nothing happens. Okay? So the neutron is taking itself out of the game entirely. Okay? So the electrical force is only involved with these particles. Okay? So, what do we conclude? What we conclude here is that if we're talking about protons and electrons, like things repel and different things attract. Okay? So this is between protons and electrons. Okay? So taking the neutron completely out of the situation, if you have a proton, it'll repel other protons. If you have an electron, it'll repel other electrons. But if they're two different particles, if you take one of each, proton, electron, they will attract. Now that's just a fact of nature. That's when you go into a lab and that's what you find. We need a way to bookkeep this. Okay? We need a way to bookkeep all this system. So what we're going to do is we come up with what is the property of this thing that is responsible, and we call that electric charge. Okay? So electric charge. So the analogy here is as mass is to the gravitational force, electric charge, which we're going to use Q for, is to the electric force. Okay? So Q, I don't know why we use Q for electric charge, but we haven't used it for anything else, and there's lots of letters already taken up by other things, so why not Q? Okay? So Q will be our variable. So mass is the property of the thing, the intrinsic property, right? Something has mass. If you have mass, you belong to a club of attracting other masses. And the interaction that you have with other masses is called the force of gravity, and it's always attractive, right? So every mass will attract every other mass. Mass is the property of the thing. So this is the property of the object, and this is the interaction that it has with other things that have it. Okay? So, we know that gravity is always attractive. Okay? And so therefore, we only need one kind of mass. We need the kind of mass that attracts all other masses. You either have mass or you don't. That's it. Well, however, here we need the ability, because to have two different kinds of interactions. We need attraction and repulsion. And for that reason, we need two different kinds of charge. So that's why there's only one type of mass, but there needs to be two types of charge. Okay? Because it isn't just everybody has mass or not. It's that in this case, you can have the kind of thing that a proton has or the kind of thing that an electron has. There are two different versions of it. And so we need a way to bookkeep that. There's two different types of charge. That's the property of the objects. And that can lead to two different types of interactions. They can be an attractive or repulsive. Can be attractive, let me just shorten it, attract or repel. Now there would be lots of ways of doing this. You can call the two types whatever you want. You can call it A and B if you want, okay? You can call it charge type, Abe and charge type Bob. It doesn't matter what you call them, but you need two types, right? So at this point, someone at some point just makes a decision. Let's call them plus and minus. It's a nice little fit, right? We need two types and we have two mathematical signs. They seem to be a nice pairing, right? Does that make sense? And there's mathematical advantages to that too, okay? So plus and minus have a mathematical relationship, but A and B do not, right? If, for instance, you have 5 A's and 5 B's, what does that mean? That's 5A plus 5B, okay? You can't do anything with that. But what we're going to do is follow the conventions that came before us. Again, this is nothing having to do with actually nature. Nature doesn't think in plus and minus. Plus and minus is a bookkeeping thing that humans are imposing upon this system. So we're just going to decide that protons are of the plus type and electrons are of the minus type. Those are our two different types of charge, and since the neutron has nothing to do with this, we might call that 0. Okay, so that's just a decision we make. So that's the type of charge, and we also have to decide on an amount of charge. Okay, the amount of charge, we're going to call it E. Now E, you might think it stands for electron, and in fact I have just used it that way. Okay, so let's clean this up. We're going to call P plus, this is positively charged, this is minus charge, positive, minus. Okay? But E is also used in a different way. Okay? E, you notice here, is used for both the proton and the electron. It obviously doesn't stand for electron anymore. What E stands for is elementary charge. Okay? So the word elementary, what does that mean? That means it's the most, like elementary school, right? It's the most basic. You can't get any more basic than that. Okay? It's the fundamental building block of charge. Fundamental building block. Okay? Now, of course, someone came up with this before someone else, then later figured out you can actually smash a proton into 3 pieces. Okay? So we're going to ignore that. Those pieces, by the way, does anyone know what they're called? Quarks. Okay? So the elementary charge at this point has a little bit of a, it's not really properly named, but that being said, no one can take a hammer and smash a proton into 17 pieces. At some point, you can't smash it into any small increments. And as is currently known by science, the electron really is elementary. You can't smash it into smaller pieces. So there, the elementary charge actually is very appropriate. Okay? So notice here that if we have that these are both the elementary charge, and one is of the plus kind, one is of the minus kind, we actually have a very nice bookkeeping system. Let's take, for instance, a hydrogen atom. A hydrogen atom is 1 proton and 1 electron. And the total amount of charge of the atom is going to be 1 of the plus E's and 1 of the minus E's, and mathematically that adds up to 0. And we have a name for that. This is called a neutral atom. Okay? Now, if we had decided to call the two charge types A or B, or Frank and Charlie or something like that, we would not have that 1 Frank plus 1 Charlie is intuitively anything. But because we've chosen this notation of plus and minus, we mathematically can see that something adds to 0. So if you move up the periodic table, okay, helium, next element, right? It's got how many protons in the nucleus? 2. How many electrons on the outside if it's neutral? 2, right? You move up and up and up and up, right? The number of protons in the nucleus defines what element it is, right? If you look on a normal periodic table, it's right there in the corner. It's how many protons are in the nucleus. And if it's neutral, it'll have the exact same amount of electrons on the outside. Now, that does not mean you can't add or remove electrons. We call that an ion, right? Okay? So if the protons and electrons are imbalanced, it's called an ion. It's not neutral anymore. The number of protons gives it the name, not the number of electrons. Okay? So, that right there, we have a nice bookkeeping system. We've called one the plus charge, one the minus charge. Whenever we have an equal number of them, we can call something neutral, and mathematically it also adds to 0. So let's take a look at what charges we can have. Let's make ourselves a little number line here. So my number line is going to look like this, and right in the middle is 0, and that is something that is neutral. Now, when I say 0, I don't mean there's nothing there. There could be a billion protons, but there would have to also be a billion electrons. Okay? In fact, you are very much a neutral object. Unless you've just spent time scuffing your shoes against the carpet, you are largely a collection of neutral atoms, right? You have just about as many protons as electrons, even though you have both of them in quantities of billions, right? So something that's neutral, it's all balanced out. You have the same number of each. Over here, we can talk about there being more protons. So let's put it like this. We'll put the protons exceed the electrons. You have more of that. And so, of course, you're going to have a net positive charge when you're on this side. You have more of the plus type than the minus type. Over here, we are on the minus side. That's when your protons are less than your electrons. Okay? So you can be out of balance either way. Okay? So the question is, can we be anywhere along this number line? And we can't. It's a ladder. Okay? You can only step in certain places. What kind of charge can you have? I guess I should label this. This is like your charge number line. You can have one electron missing, for instance. Then you have one excess proton. Okay? You can't be anywhere in between. Right? You can be here, you can be here. How do you get something like that? You can't. Now again, don't worry about the quarks. The quarks, maybe you could have a couple steps in between, but you can't be anywhere you want. The next rung on the ladder is you have an imbalance of 2, right? You either have 2 extra protons or 2 missing electrons. There's some reason why you have the imbalance being 2. You can see that these are steps on a ladder. Same thing over here. You can have 1 electron extra, or 1 or 2 electrons extra, but you can't have an electron and a half. Can't be done. So this is the first quantity, which is what we call quantized. And what quantized means is that it can't have any value. It's not continuous. There are steps to the ladder, and you can only be on the steps. You can't be in between. Okay, so charge is quantized. And quantized is the opposite of continuous. Okay, it cannot have any value you want. That, in fact, is the best way to test if an amount of charge is permissible. Okay, is to take the amount of charge that you have, divide it by the elementary charge, and you had better get an integer. Because when something has a net charge, it's ultimately formed by an imbalance between protons and electrons. So if you take the amount of charge you have and you divide it by the elementary charge and you get 7.2, how do you get 0.2 of an electron or something, right? You can't. If it doesn't satisfy this, the amount of charge is not allowed, okay? It doesn't make sense. That's how charge is made. Charge is made by imbalancing these two things, okay? So that's a permissible amount of charge. If it doesn't satisfy this, it's not right. It doesn't matter what integer comes out. If a very large integer comes out, like 7 billion, that's fine. 7 billion is an integer. That means you have 7 billion more of one thing than the other thing. But you can't come out with something that's not a whole number, okay? So, now let's move forward to how, what is the SI unit for charge? The elementary charge is the fundamental building block, but as you probably know, we have a particular set of units that we use in the class. Okay? Over here. So SI units. This is what we usually use in physics. If we want to talk about a length, what do we usually use? Meters. If we want to talk about a mass, what do we usually talk about? Kilograms. How about time? Seconds. Angle, we usually use radians, right? Angles in terms of pi. That one we often cheat and use degrees, but if you really want to get serious, we use angles in terms of pi, right? So those are the 4 SI units we use in Physics 1. And these were our fundamental units, right? These were like kind of our things that we started off with. We did them in the first lecture of Physics 1. And then we, of course, came up with a bunch of composite units for those, okay? So those are combinations of those. So for instance, the units of force, what do we measure force in? Newtons. Newtons. Now Newton was just a kilogram meter per second squared, right? So it's a combination. Does anyone remember what we measured work and energy in? Joules. Joules, right? And so on and so forth. So we have composite units, which are just convenient abbreviations of groupings of the fundamental ones. Physics 2. The only fundamental unit we need is to add the SI unit for electrical charge. It's called a coulomb. Capital C for short. It's the SI unit for electric charge. And that is going to be added to our fundamental list of units. That's it. There are no more. There are no more that we add for Physics 2. Coulomb, along with the Physics 1 unit, fundamental units, can make everything we need. Now don't get me wrong, we'll make lots of composite units that include the coulomb, things that you may have heard of. For instance, a volt. You ever heard of voltage? Right? That is a composite unit that happens to include a coulomb. Okay? An ohm, a unit of electrical resistance. These are composite units that happen to include, mixed in with other things, a coulomb. So, we need to establish what is the SI unit and how does that compare to the elementary charge. So, let me tell you right now about how that relates. 1 meter is, you can get your head around a meter. It's about this much, right? It's picked as a standard because it's kind of a everyday length you can see with your own eyes. It's not gigantically huge or tiny, right? It's 1 is 1, right? 1 is something you can work around. 1 kilogram you can hold in your hand. 1 second you can watch tick off the clock, right? 1 radian is not a gigantic amount of angle, okay? Coulomb, I have to report, is not an everyday amount of charge, okay? 1 coulomb is actually a huge amount of charge. For instance, when a lightning bolt hits the ground, that might be an exchange of like 5 coulombs, okay? 1 coulomb is actually larger than every day. 1 coulomb is a larger than everyday amount in many ways. Now, why would you do that if you're trying to set up a nice unit set? Why would you do that? Well, it turns out that coulomb is often not what you worry about. There are other units that you worry about that are more reasonable. Okay? But particularly because 1 coulomb is not even an everyday amount, it's more than an everyday amount. When we start going down to the elementary charge, you better believe that that is going to be the tiniest fraction of a coulomb. In fact, one elementary charge is 1.6 times 10 to the minus 19 coulombs. Okay? Hopefully not surprising. If we go down to the most smallest fundamental building blocks of matter, that's going to be the tiniest little fraction of the coulomb which is used for the SI unit. And so I want to point out that 10 to the minus 19th, this is an incredibly tiny fraction. And so when I go back over here, and I was talking about my ladder, right, my ladder of charge, and you can only step on the whole steps, you can't step in between. I want you to appreciate how small these steps are, okay? These steps are on the order of 10 to the minus 19th. These steps are each 10 to the minus 19th coulombs. They are very small steps. So if you were to try to draw that on a standard number line, it would kind of look like this. You can step here, or here, or here, or here, or here, or here. It starts to look like you can step anywhere because the steps are so small. The analogy I like to use is with grains of sand, right? We like to think of sand as a continuous thing, right? If you have any bucket or container, you can fill it up with sand exactly, right? You think of sand as you can have any amount you want. Maybe to an ant, right, grains of sand look big and can't be split up. So you can roll 1 grain of sand to your ant house, or you can roll 2, but you can't take a grain of sand in half. So to an ant, it looks like ladder, and the quantization's a big deal. But for us, oftentimes, we totally forget about that. We totally tend to think of charge as continuous, even though it's not, because it's granular, but on such a small level. Okay? So remember, even though we are going to start to think of it as kind of a continuous thing, if you ever need to check if something's allowed, make sure it's an integer increment of the elementary charge, because if not, you've violated, you've split an electron in half. Okay, so that's it for today. We'll pick up on, now that we know the charge, that's the intrinsic property of things, we need to then say how do they interact with other charges, that's the force, and we'll introduce the force law, which is called Coulomb's law. So we'll do that next time.